the gas law that relates, the PV equals nRT gas law that relates the pressure, volume, number of moles, and temperature of a confined gas from one state to another has been somewhat illustrated by the experiments that we've done. Let's define these quantities and then see how it is that we've observed this law, or some aspects at least of this law. Okay, a mole, incidentally, you should know this from prerequisite courses and so forth, maybe not, but your text tells you a mole is a number of particles. It's approximately 6.023 times 10 to the 23rd, maybe it's 0.022 actually, so check that out in your text. Never trust the accuracy of anything I say here. The concept's usually right. The numbers can sometimes be wrong. And we'll incidentally note that the mass of a mole is equal to, of a mole of a element is equal to its atomic number. If it's a chemical compound, then it's the molecular mass, which is obtained by taking the molecular formula and using the atomic numbers of the various constituents in a way that's fairly obvious. So we're not going to get into all the details of that. I'm not going to get into those. You will need to know some of that to do the problems in your text, but it's fairly simple, fairly obvious. In any case, P is the pressure, V is the volume of the gas, N is the number of moles present, and T is the temperature. Now we know that if we have a confined gas and vary these quantities, these variables, but we vary these quantities, other quantities will change. For example, if we hold the temperature constant and don't add any gas, don't let any gas escape, if we increase the pressure, the volume is going to go down. Matter of fact, we saw that in the experiment. We heated the water up, it increased the pressure on the air column. In the air column, now the air column didn't heat up. The temperature of the gas in the bottle changed, but that didn't change the temperature of the air in the column. In any case, the air in the column changed temperature, changed pressure, and the volume changed. Greater pressure, less volume. And if we change the volume by compressing it, of course that increases the pressure. Of course that usually increases the temperature also, so we've got to be careful about how these things change. Okay, in any case, we have the law that says PV equals nRT, and we're going to talk about how to interpret that a little. R is just a constant. It's always the same. It's 8.31 joules per mole Kelvin. And incidentally, temperature is absolute temperature. It's Kelvin temperature measured from absolute zero, not Celsius temperature. Okay, so in the experiment, when we looked at the air column, N was constant. There were no leaks, and there was no way for air to get into that column. T was approximately constant because that column stays very close to room temperature unless you somehow get it close to a heat source. So what we have is PV equals nRT. N is constant, T is constant, R is always constant, so we have PV equals something that's constant. We multiply three constants together, we get a constant. So that the pressure is equal to whatever that constant is divided by the volume. Now, in state 1, and let's take state 1 as the state of the air in the column before we heated the water up, or before we heated the gas in the bottle up. The pressure was P1, let's say, and the volume was V1. Afterwards, after heating the air in the bottle up, the air in the column was at pressure P2 and volume V2. Since pressure times volume is constant, P1 V1 had to equal P2 V2. The P1 V1 product for state 1 before is equal to the P2 V2 product of pressure and volume for the state after the expansion. Since P1 V1 equals P2 V2, we can algebraically rearrange this in a very simple way, and we get P2 over P1 equals V1 over V2. Now, for the gas in the column, we had a uniform tube, a uniform column of gas, a uniform cross-section to that column. The ratio of volumes is just equal to the ratio of the lengths. Since the volume is equal to the cross-sectional area times the length, and the cross-sectional areas are the same, volume 1 is area times length 1, volume 2 is area times length 2, and the ratio is just length 1 over length 2. As a result, the pressure has a ratio L1 over L2, so that P2 over P1 equals L1 over L2. This follows pressure 2 over pressure 1 is volume 1 over volume 2, which is L1 over L2. So P2 over P1 is the ratio of the lengths, and of course that's something that we use in analyzing the experiment.